This is Mr. Anderson from Kellogg Community College, and we are going to be looking at Section 6 of Chapter 9, Solving Exponential and Logarithmic Equations. This is going to be where we solve for x, and sometimes the x is going to be the exponent of a problem, and sometimes the x is going to be in the log of it itself. So sometimes we're going to be finding that log right there given a problem such as this, or maybe like this, where we can find the value of x as long as x is positive, because the domain of any logarithm is greater than 0, the domain of any exponential is real. So just keep that aware, be aware of that as we go through the later part of this worksheet when we are actually solving for x inside of a logarithm. Now, the principle of exponential equality says that if we have b to the x equal to b to the 9, then or b to the y, then x is equal to y. This can be illustrated if we look at problem number 1. 64 is a power of 2. Now, this isn't always the case. If you look at problem 2, you'll notice that 24 is not a power of 2, but 64 is a power of 2. 64 can be written as 2 to the 6th power, because 2 to the 6th is 64. And that would make this problem have the same base. So, like this principle of exponential equality, b to the x equals b to the y, now I have 2 to the 3x equals 2 to the 6. So 3x is equal to 6, or x is equal to 2. When we get to a problem like this, where we don't have 24 being able to be written as the power of 2 very easily, what we can use is the change of base formula. The change of base, this is an equivalent to writing log base 2 of 24 equals x. Because when we have an exponential, the logarithm puts it into this question: 2 to the what power is 24. And using our change of base formula to find x, we're going to take our log of 24 divided by our log of 2. And since we have a calculator, we can do these pretty easily. Just make sure to put the parentheses after the 24 before you divide it by 2. And here we get an answer of x being equal to 4 and 585 thousandths, since we're rounding to 3 decimal places. Now let's apply that to problem number 3 here. Now problem number 3 is going to use the principle of logarithmic equality. To give you that, the principle of logarithmic equality is if you have log base a of x equals log base a of y, then x is equal to y. What this really means is that you can take the log of both sides. So if I'm trying to get rid of the 5 and just maybe get to my x plus 2, what I can do is take the log of base 5 on both sides. It changes the system that we're in. Instead of this being an exponential, we've converted this to a logarithm. But what we have is some simplification, because log base 5 of 5 is equal to 1. The x plus 2 can be brought out to front like this, x plus 2. So essentially this becomes x plus 2 times the quantity of 1, so this just leaves me with the x plus 2. If you don't know if you don't know all of those steps there, some people look at this as a canceling technique, but it's really not canceling. It's multiplying to make 1 and we bring the exponent out front. But you can still probably operate with that misconception and get the problem right. So log base 5 of 15, we got to use our change of base formula here, and the change of base formula will be then log of 15 divided by log of 5. So this x plus 2 becomes this change of base formula. Anytime you have a log of a numerical base of a number here, we can use change of base to get a decimal. And this is going to be 1 and 683 thousandths. If I subtract 2 from both sides, I get negative 317 thousandths. And since the x was an exponent and the exponents have a real domain, we can have a negative number for my x. For number 4, if we're going to try to simplify this e, we have to take the log of both sides, but the log of base e is the natural log. The natural log and logs are inverses of each other. So these two simplify to make, again, the the 100th t times 1 is equal to the natural log of 100. We can type that into our calculator and get approximately 4/605 thousandths. Then we divide both sides by the negative 100th, and t is equal to negative 460 and 5/10, or half. So we're going to see this technique used more and more, where we're going to be trying to get rid of either the log or e or any kind of our exponents here. Now these problems are going to go pretty quickly. So if we take a look at number 5, we're going to divide both sides by 3 to get the e all by itself. So the 3's simplify here. So 29/3, I'm going to resist turning this into a decimal because of what I'm about to do next. Because what I want to do is get the 2x by itself. So if I take the natural log of both sides, since the natural log is the log base e of e simplifies to 1, and the 2x is brought out in front using our power rule. The natural log of 29/3 is going to be 2 and 269 thousandths. Dividing both sides by 2, x is equal to approximately 1 and 134 thousandths if you rounded this number. Then we get to problem 6. And from what I'm about to do in problems 6 through 9 in the rest of the worksheet is another application of the principle of logarithmic equality. We want to try in this problem to get rid of log base 2. Now, of course, you could rewrite this as an exponential. 2 to the 6th power equals x, so 64 equals x. But what if that just slipped your mind? There's got to be a way to try to get, well, in our mind, to cancel this log base 2, but really we're not canceling this. We're just going to try to get the x by itself. So if we take both sides to the power of 2, and this is looking at our principle of exponential equality, what this does is it gives me a way to simplify this. 2 raised to the log base 2 of x just gives me x. Now there is a little bit of a proof like that in the book. You can kind of see where they're changing this into x, and I would like you to refer you to the book for that, since the problems that we're about to get into are going to get pretty long for this worksheet. So this simplifies to 1 times x, which is just x, and 2 to the 6 is 64. Now what this is going to allow us to do is if we need to get rid of a natural log, we're just going to take this inverse of the natural log, which is e, and that e and the natural log of x simplify down to 1 times x. E to the 4th power we can type into the calculator, and it's approximately 54 and 598 thousandths. So if we want to try to manipulate this to get x by itself, we're going to take everything to the base 10, because the base 10 here, because log without a number written is log base 10. So this simplifies to 1 times x, and this 10 to the 6/10 is approximately 3 and 981 thousandths. Finally, right here, if you apply base 10 to this, because log without a number written is base 10, so this makes x, and 10 to the 1st power is 10. So this problem was really asking base 10 to the 1st power is what, and that would be 10. Okay, so let's take a look at the tougher problems on the back of the worksheet here. Number 10 is pretty straightforward. Number 10, what we're going to do is we are going to get, to try to get this 7 minus 2x by itself. So we're going to take everything to the base 5. 5 raised to the log base 5 of 7 minus 2x is 1 times 7 minus 2x. And 5 to the 3rd power is not 15. 5 to the 3rd power is 125. Please watch those mistakes. We subtract the 7 from both sides, so negative 2 is equal to negative 59. Divide both sides by negative 2. Oh shoot, I made a mistake here. I went too far to the answer here. If I subtract 7 from both sides, sorry about this here, 7 minus 2x equals 125. If I subtract 7 from both sides, I get negative 2x equals 118. Divide both sides by -2. X is equal to -59. Now, I've said before that the domain of the log has to be greater than 0. And here I have a situation where x is equal to a -59. If I plug the -59 back into this equation, though, what I get is I get my positive 118, and then that positive 118 and the 7 make 125. Since plugging my negative x back into my log makes it positive, this is an okay answer. If there's a situation where I plug my x back into my log and the log is negative, then I cannot accept that as an answer. If I look at problem number 11, before I take everything and change to the base 10, I really have to get log on one side because if I can't just put a 10 underneath all of these since this is a binomial. So let's make this one term here. So this is the log of x divided by x plus 7 equals -1. Now, since this is a monomial and this is a monomial, I can do this. I can go 10 and do this to both sides here. So 10 raised to the log base 10 of x over x plus 7 will simplify this to x and x plus 7. 10 raised to the -1 power is 1 over 10. You could use a decimal here, but I don't suggest it. It's actually easier if you use this because we can now cross multiply here. We can go x plus 7 times 1, which is x plus 7, and x times 10, which is 10x. We can solve for x, move the x to the other side, so this is going to be 7 is equal to 9x. Divide both sides by 9, so 7/9 equals x. Or if I'm still rounding to 3 decimal places, or the thousandth, this is going to be x is equal to 0.778, or 778 thousandths. Now, what's nice about this is if I plug that into the equation, you can see that they will be positive. So you can see where I'm going to have a positive number if I put 7/9 here, and 7/9 plus 7 is still positive, so this checks out as an answer. All right. Now in this problem, I have a binomial on this side here, and I have a monomial on this side. To get my monomials together, I'm going to have to move this to the left, and that way I can combine this to make one log. So log base 2, x plus 3, is subtracting log base 2, x minus 3, and set that equal to 4. Now I'm going to then stack this up here to x plus 3 over x minus 3 inside of log base 2 and set that equal to 4. Now to get the x plus 3, x minus 3 by itself, I'm going to take everything to the base 2 here. So that gives me my 1 times x plus 3 and x minus 3, and 2 to the 4th power is going to be 16. Now I'm going to put that over 1 because I want to cross multiply like this. So 16 times x minus 3 is 16x minus 48, and x plus 3 times 1 is just x plus 3. I move my 48 to the right, which gives me 51. Move my x to the left, gives me 15x. Divide both sides by 15, and so x is equal to 3.4, or 3 2/5. Now the 3.4 is positive, so if I plug in the 3.4 into the first or second parenthesis here, I will get a positive number. And that means that this will check out and doesn't violate my domain rules. My domain of this problem has to be positive. So when I have my 3.4 into this expression, this is a positive 0.4, so it checks out. All right, number 13. Common mistake is when someone just says, well, I'm just going to put, 4 underneath all of these here, but we really should get these together so they form a monomial. So what I'm going to do is erase this and kind of reset my problem here. Kind of reset all 3 of these so we can see them all at once. Okay, so what I have to do is I have to get this left-hand side to get simplified down to 1 log, and that way we can take a look at getting, or at least simplifying to get the log base 4 out of here. Now, since these are getting added, then this becomes x plus 2 and x minus 7 all within the log base 4. So that's technically together now because using our product rule, the product rule means we can add these up. And then over here we've got log base 4 of 10. Using Using the principle of exponential equality, what we can now say is that since these are both log base 4, we can take all of these with an exponential of 4, and that will simplify this to 1. So now I have x plus 2 times x minus 7 is equal to 10, because this is 1 times 10 and 1 times this FOILed binomial. Now this goes back a couple chapters. How do we solve for x here? Well, what we're going to do is we're going to solve for x by FOILing this out, moving the 10 over, and then we're going to factor again to see what answers we can get. So this is going to be x squared minus 7x plus 2x minus 14 minus 10 equals 0. So just to slow down and tell you what I did there, I did my FOIL, so x and x and negative 7, 2 and x, 2 and negative 7, and then we moved the 10 to the other side, so it became a negative 10. Then let's move up here, and we've got x squared, and we have minus 5x, and then we have minus 24 equals 0. Now we could use quadratic formula to solve for x, but it's much faster factoring. Can you think of two numbers that multiply to make negative 24 and add to make negative 5? Negative 8 and positive 3 makes a negative 24 when you multiply them and a negative 5 when you add. This means I have an answer of x minus 8 equals 0, or x is equal to 8, and here x plus 3 equals 0, or x is equal to negative 3. Now this is not an acceptable answer. The reason why is because I've put negative 3 plus 2 into the problem, or negative 3 minus 7 into the problem, I get a negative log. The x inside of the log is negative, so that means it doesn't work because it breaks the domain restrictions that the value of x is anything inside of these has to be positive. So x equals 8 is the correct answer to the problem. Problem 14 is going to be very similar, except that on the right hand side you'll notice that this is, instead of saying log base 4 of 10, this is just a number 2. So we're going to put this together like we did above. So log base 3 parentheses x minus 4 and then x plus 4, which also happens to be part of the, this would be a factored difference of square problem here, and this is equal to 2. If we now take our 3 and make that the base power of this, 3 taken to the log base 3 of this is going to be 1 times x minus 4 times x plus 4, and 3 to the second power is 9. If I FOILed this, I'd get x squared minus 16 equals 9. It is possible to do this one of two ways. One way you can do it is move the 16 to the right, and another way you can do it is move the 9 to the left. Just for a change of pace here, I'm going to move the 16 to the right. So this is going to be x squared is equal to 25. That's adding the 16 to both sides. Now, I do want to say though that if you do factor out or FOIL out x minus 4, x plus 4, you will get a plus 4x and a minus 4x that will give you 0x. So that's why this x squared minus 16 was quickly answered from this. This is a difference of squares. Now, going back to this, a lot of people make a mistake because when they take the square root of both sides, they forget that you can have plus or minus 5. But if you make a simple mistake and forget the negative, that's okay in this problem. You got dumb lucky, because when you have two answers to this, we can't accept the negative, because if we plug the negative into this problem, it'll break our domain rule. Our domain rule says that we have to have logarithms when solving for x inside of the parentheses there. We got to have the domain greater than 0. So 5 plus 4 and 5 minus 4 is they're both positive, so that works, but the negative 5 will not work. So let's move on to problem number 15, our last problem today. Let's put this together. So we got our x plus 6 over x, and here we have our log base 4 equals 2. What we'll then do is, make everything 4 to the power of, and that way that will simplify this to 1 times x plus 6 over x, and 4 squared is 16, not 8. Common mistake when people get to a problem like this, they'll say 3 squared is 6 and 4 squared is 8. It's not true. Just be careful, don't get sloppy. So we go 16 times x, which is 16x, and the 1 times x plus 6 is just x plus 6. Subtract the x, 15x is equal to 6. Divide the 15, so x is equal to 6/15. Please simplify that to 2/5, or 0.4. That's important because we just don't want you to get all the way to the end and then mess up on just a simple fraction. And if we plug that fraction back into this problem, you'll notice that it still keeps the domain nice and happy. And that, my friends, is the end of section 9.6. Thank you for watching.